Section: Introduction. In this section, we delve into the exciting developments in generative AI technologies that are creating what's known as the synthetic data age. This era is characterized by our increasing interaction with data produced by large-scale models like GPT-4, Stable Diffusion, and their successors. A significant factor in the success of these large models is their ability to learn from vast amounts of data from the web. We've observed that as these models are fed more data, their performance improves according to specific patterns, known as scaling laws. These laws show that errors decrease as the amount of training data increases, and new abilities emerge as the scale of data expands. However, our understanding is still evolving, especially regarding the future implications of models trained on data they or their predecessors have generated. Some studies suggest this could lead to a phenomenon known as model collapse, where the learning process significantly deteriorates. Scaling laws have been a focal point in various machine learning domains, including speech, translation, vision, video, and solving mathematical problems. These laws indicate that the error rate decreases in a predictable manner as we increase the amount of training data, the size of the model, and the computational power. Theoretical foundations for these laws have been established, particularly for models similar to large language models, LLMs. This relationship between scaling and the emergence of new abilities supports the idea that scaling up is crucial for advancement. Regarding model collapse, current LLMs like GPT-4 and image generation models such as DALL-E and Stable Diffusion are trained on massive datasets of human-generated content. As the web begins to fill with synthetic data indistinguishable from real data, our training datasets are becoming a mix of real and synthetic content. This mix could lead to a significant decline in model performance, a situation referred to as model collapse. This phenomenon has been observed empirically and is beginning to be understood theoretically, highlighting the risks of training models on data they have generated. We also explore how the distribution of data affects the scaling behavior of LLM-style models. Typically, these models assume a heavy-tailed distribution of input features, which is common in natural datasets. However, when models are trained on such data, the generated data might alter the original distribution by cutting off or narrowing its tail. This alteration could be due to the model's generation algorithms or finite sampling bias. Our main contributions include establishing new scaling laws that help explain the phenomenon of model collapse in simplified models. We've conducted large-scale experiments to test these theories, such as fine-tuning an LLM on a dataset derived from Wikitext 103 and training transformer models to predict the greatest common divisor. Our findings suggest that training models on AI-generated data alters the true data distribution, either by cutting off the tail at a certain point or narrowing the tail to a smaller exponent. These insights contribute to our understanding of model collapse and the impact of synthetic data on the future of AI. Section Summary. In this section, we introduce groundbreaking advances in generative AI algorithms that are leading us into the synthetic data age, where models like GPT-4 and Stable Diffusion are generating data at an unprecedented scale. We discuss scaling laws in machine learning, showing how larger models exhibit new abilities as they consume massive amounts of training data, and we highlight the emerging concern of model collapse, as models are trained on a mix of human-generated and synthetic data, potentially leading to significant deterioration in model performance. Section 2. A triplet scaling law for memory-limited models. In this section, we delve into a few key areas of our study, starting with the discovery of a new scaling law for models with limited memory. We explore a straightforward associative memory model and uncover a scaling law that essentially says the capacity of the model, which we measure by the embedding dimension, grows according to a specific rule. This rule is influenced by both the complexity of the problem being solved and the algorithm used to update the model's memory during training. Next, we discuss the phenomenon of model collapse when AI models are trained over multiple generations, each using data produced by the previous one. We found a universal principle that shows the usual test error, which is the error rate when the model is trained on clean, non-AI generated data, changes in a predictable way. This change can be thought of as a degradation that multiplies with each generation. In simpler terms, as we train AI models on data from previous AI models over and over, the quality of learning degrades significantly. This could lead to a future where the internet is so full of AI-generated content that finding clean data to train models becomes very difficult and expensive. To counteract this, we've discovered that mixing even a small amount of clean data with AI-generated data can prevent model collapse. This introduces what we call a grokking phenomenon, where the model suddenly improves in performance after a period of stagnation. The duration of this stagnant period depends on the proportion of clean data in the training set. If there's no clean data at all, the model never moves past this plateau. However, even a tiny amount of clean data can break this cycle, leading to continued improvement. This effect is particularly noticeable in models trained on deterministic tasks, like arithmetic, where we've seen it firsthand in our experiments with transformer models designed for greatest common divisor tasks. However, this grokking phenomenon is less pronounced in tasks with more variability in the correct answers. We also take a moment to place our work in the context of existing research. Scaling laws have been a topic of interest in various domains, from non-parametric models to those focusing on memorization with discrete data. Our triplet scaling law builds on recent findings in the field of associative memories with limited capacity. Furthermore, the issue of model collapse in the era of synthetic data has begun to attract attention, with studies pointing to the narrowing of data variance and the approximation errors as key factors. Our work adds to this conversation by providing both theoretical and empirical analysis of how model collapse can be understood through scaling laws and the emergence of new abilities in AI models. Lastly, we introduce the foundation of our theory with a model that assumes infinite memory and a deterministic approach to labeling data. This model, inspired by the Hutter LLM, serves as a starting point for our exploration. We also discuss how the distribution of tokens, following the Zipf law, can be interpreted through the lens of the quantization hypothesis, suggesting that each token represents a discrete skill with varying frequencies of occurrence. This perspective helps us understand the distribution's long tail, which is controlled by a shape parameter, indicating that larger values correspond to a wider range of less common skills. Section Summary. In this section, we introduce a new scaling law for memory-limited models, where the embedding dimension represents model capacity, and the exponent is influenced by the model's architecture and memory update algorithm. We also explore model collapse over multiple generations in AI data generation recursion, showing that mixing AI-generated data with a small amount of clean data can mitigate model collapse by introducing a grokking phenomenon, which halts error increase and allows for continued learning. Additionally, we discuss strategies to curate data and identify scenarios where adding AI data can be beneficial, emphasizing the importance of incorporating clean data to prevent model degradation over time. Section: What causes model collapse? In this section, we explore the reasons behind model collapse, focusing on two main phenomena: tail cutting and tail narrowing. Let's start with tail cutting. We've noticed that making specific choices in the AI generation algorithm, such as selecting only the top 10 or 11 predictions for the next token, effectively ignores less common outcomes or skills beyond the 11th most frequent ones. This is a form of tail cutting. However, tail cutting can also happen unintentionally due to the limited size of the training set, which we refer to as sampling bias. Imagine we have a dataset of a certain size, say 21 samples. When we use this dataset to estimate a distribution, the process itself can lead to tail cutting. Essentially, if a particular value appears in our dataset a certain number of times on average, it means our estimated distribution will only consider outcomes up to a certain rank, effectively cutting off the tail beyond this rank. Moving on to tail narrowing, we observe that this phenomenon can occur during AI generation as well. One way this happens is through lowering the temperature during next token prediction. To put it simply, when we adjust the temperature in our model's predictions, it can lead to a more narrow selection of outcomes, thus narrowing the tail of the distribution. Other factors can also contribute to tail narrowing, such as the specific characteristics of autoregressive models. We also introduce a new scaling law related to the Hutter Large Language Model, LLM. When we train a model on a dataset sampled from a specific distribution and then test it on the original data distribution, the test error follows a certain pattern. If we modify the original distribution by cutting off the tail beyond a certain point and then train and test the model using this modified distribution, we observe a specific scaling law for the test error. This law shows that as the size of the AI-generated sample increases, the performance of the downstream model eventually plateaus, indicating that collecting more AI-generated samples won't lead to better performance. Furthermore, we discuss the impact of tail narrowing on scaling behavior. Unlike tail cutting, which leads to a performance plateau, tail narrowing results in a slower decay rate in performance. This means that the model's performance decreases more gradually as we train on AI-generated data with a narrower tail. Lastly, we examine how model collapse can occur over multiple generations of AI data. By recursively generating AI data and observing the scaling of test error, we find that model collapse happens under certain conditions related to the loss scaling linearly with the number of generations. This analysis helps us understand under what circumstances model collapse is likely to occur and how it can be influenced by the number of data generations and the specific characteristics of the AI-generated data. In summary, our exploration into what causes model collapse reveals the significant roles played by tail cutting and tail narrowing, introduces a new scaling law in the context of Hutter LLMs, and highlights the cumulative impact of these phenomena over multiple generations of AI data. Section Summary. In this section, we explore the causes of model collapse, focusing on two main factors: tail cutting and tail narrowing during AI generation. Tail cutting occurs due to deliberate choices in the AI generation algorithm or the finite size of the training set, inducing an effective tail cutting effect. Tail narrowing, on the other hand, is influenced by mechanisms like lowered temperature during next token prediction, resulting in a narrowing of the tail during AI generation. These effects can lead to a loss of scaling in downstream models, ultimately resulting in model collapse, especially when considering multiple generations of AI data. Section: Mitigating model collapse via data mixing. In this section, we delve into how adding even a small amount of real data to a dataset primarily composed of AI-generated data can prevent what's known as model collapse. We examine two key observations. First, when we mix a small portion, specifically 37% of the original data, with a larger portion, 94%, of AI-generated data, we encounter an intriguing, grokking phenomenon. This phenomenon shows that the model's test loss stops worsening with more training data and eventually starts to improve, following the original model's expected improvement pattern. Second, we look into the idea of adding data to make up for what's missing at the tail of our data distribution. However, we find that this approach requires precision. Adding data from too far into the tail doesn't help, but adding data from just before the missing tail section can be quite beneficial. To address the issue of a cutoff tail and its impact on model performance, we suggest adding carefully selected data that highlights the tail end of the distribution. Our findings suggest that if we add data from too far beyond the tail, deep in the tail, it won't help. Instead, we need to target our data addition efforts to just around the area of the tail that's missing, within a specific range, to see an improvement in model performance beyond the initial plateau. Imagine we acquire a segment of the real data distribution's tail. Let's say the distribution is supported on a certain range. As certain parameters grow infinitely large, we observe a clear phase transition effect. Specifically, if we add data from just the right part of the tail, we can completely counteract the negative effects of using AI-generated data that lacks this tail. However, if we add data from too far into the tail, it doesn't help at all. We also explore a grokking phenomenon related to the issue of tail cutting. By mixing a small amount of real data with AI-generated data that lacks part of the tail, we see that initially, the test error doesn't improve, suggesting that the investment in real data doesn't pay off immediately. However, after reaching a certain point, the test error starts to decrease, indicating that the model begins to follow the expected scaling law of performance improvement, albeit at a higher cost for data. This suggests that even a tiny amount of real data, no matter how small, can lead to significant improvements in model performance as training progresses. Furthermore, we confirm this grokking phenomenon through experiments with transformer models trained on specific tasks, indicating that this approach could be beneficial for a wide range of models, especially those dealing with deterministic tasks. Lastly, we discuss how AI-generated data, under certain conditions, can actually enhance model performance up to a point, after which its benefits level off. This finding could help us understand why, in some cases, incorporating AI-generated data into the training process results in better models, particularly when the AI-generated data comes from a more advanced model. In summary, our exploration into mitigating model collapse through data mixing reveals that carefully adding real data to AI-generated data can significantly improve model performance, especially when done with precision and understanding of the underlying data distribution. Section Summary. In this section, we explore how adding a small amount of original data from the true distribution alongside AI-generated data can mitigate model collapse. By mixing fractions of original and AI data, we observe a grokking phenomenon where test loss plateaus and then decreases, following the scaling law of the original model. Additionally, we investigate the impact of acquiring data from the tail of the original distribution, highlighting the importance of carefully curating data from the precise, missing tail to enhance model performance beyond plateaus. Section: A tailed bigram model. In this section, we delve into a more intricate model that brings us closer to understanding the probabilistic and autoregressive nature of language models, which are designed to predict the next word in a sequence. We outline the process of generating data, introduce a new model we refer to as Hutter++, and confirm that the original scaling law, which applies when using clean data, remains valid. We also explore how this scaling law behaves when applied to AI-generated data. A crucial initial step involves shifting from deterministic predictions to probabilistic ones. Instead of predicting a single next word with certainty, we now consider a range of possible next words, each with a certain probability that decreases according to a power law. This change acknowledges that the likelihood of the next word can depend significantly on the word that comes before it. We model this by associating each preceding word with a permutation that dictates the probable order of subsequent words. Essentially, we treat the data as pairs of words, where the distribution of the first word is determined as before, but the second word is chosen based on a probability distribution. By generating sequences one step at a time, using the previous output as the next input, we make the model autoregressive. Each pair of successive words is treated similarly to the pairs mentioned earlier, with the difference being that the distribution governing the first word of each pair changes over time. We do not make any specific assumptions about this distribution beyond a basic technical condition. We then introduce the Hutter++ algorithm, an enhancement of the original Hutter model that is tailored for pairs of words, known as bigrams. The algorithm calculates the frequency of each word pair in the dataset and uses these frequencies to estimate the probability of each bigram. This estimation is based on an independent and identically distributed sample of a certain size. For theoretical analysis, we use a test error metric that relies on the total variation distance, a measure of how one probability distribution diverges from another. This metric is particularly useful because it can be controlled and is related to the Kullback-Leibler divergence, suggesting our findings might also apply to autoregressive models that use perplexity loss. We also establish a scaling law for the Hutter++ model, showing that under certain conditions, the model behaves similarly to the classical setup, even when outputs are not deterministic. This is significant because it suggests that the model's performance can scale predictably with changes in certain parameters. However, we also address the issue of model collapse in probabilistic settings, where the model might fail to distinguish between different types of data or produce overly simplified outputs. We examine conditions under which this collapse occurs and propose solutions to mitigate it. Furthermore, we extend our analysis to autoregressive big RAMs and demonstrate that our results are empirically supported. We also discuss the phenomenon of grokking, a sudden leap in model performance after additional training, in the context of models trained on mixtures of clean and synthetic data. While the traditional grokking phenomenon does not fully apply in probabilistic settings, we observe a similar, though smoothed, S-shaped scaling law. In summary, this section explores the transition to a more complex model that better captures the probabilistic nature of language, introduces the Hutter++ algorithm, confirms the persistence of scaling laws in probabilistic settings, and discusses the challenges and peculiarities of model performance in these contexts. Section Summary. In this section, we delve into a more intricate model, aiming to capture the probabilistic and autoregressive aspects of language models, LLMs, for next token prediction. We define a new model, Hutter++, which maintains the scaling law observed with clean data but also demonstrates a loss of scaling with AI-generated data. By introducing probabilistic ground truth labels and an autoregressive approach, we model the dependency of the most frequent next token on the preceding token, paving the way for generating sequences step by step. Section: Capacity-limited memory models, a triplet scaling law. In this section, we explore an extension of the Hutter LLM that incorporates a finite memory, allowing us to examine how models behave when they have a limited capacity to store information. We delve into the phenomenon known as model collapse through a simple associative memory model that resembles a transformer but with finite memory. The concept of capacity in our model is represented by a specific integer value, which essentially dictates how much the model can remember. We introduce an unknown function, which could be something like taking a number and finding its remainder when divided by another number. This function plays a crucial role in how our model processes information. Additionally, we use a probability distribution to represent a learner that is estimated from a sample of data. This learner is designed to remember input and output pairs it has encountered, with certain memories being prioritized over others based on their weights. To improve the model's memory capabilities, we suggest using random embeddings from a uniform distribution. This approach allows us to establish a general scaling law that relates the model's performance to various parameters, such as the sample size, embedding dimension, and a frequency cutoff. This scaling law, which we refer to as the triplet scaling law, has been both theoretically predicted and empirically confirmed, showing its applicability to different data types and demonstrating the universality of certain phenomena like loss of scaling and grokking. Moving on to our experiments, we aim to provide empirical evidence supporting our theoretical predictions. We examine 4 scenarios of increasing complexity, starting with an empirical version of the Hutter model and progressing through autoregressive bigram models, a transformer model designed to predict the greatest common divisor, GCD, of 2 integers, and finally, a large-scale language model trained on a vast dataset. Our experiments reveal a pattern of scaling loss and model collapse across different generations of models, confirming our theoretical insights. For instance, in our initial model trained on a specific number of samples, we observe a significant decline in performance as we generate new data from this model and use it to train subsequent generations. This pattern persists across different settings, including when we apply mechanisms like temperature scaling, which are commonly used to influence the distribution of generated data. In the case of the transformer model learning to predict the GCD, we notice that the model acquires new skills in bursts, which can be seen as learning new GCDs and their combinations. However, when trained exclusively on data it generated, the model exhibits a tendency to forget previously learned skills, a phenomenon we refer to as unlearning, alongside a grokking effect when trained with a mix of real and generated data. Lastly, our experiments with a large-scale language model, Llama 2, involve fine-tuning the model with synthetic data generated in a controlled manner. We observe a decay in the scaling law over several generations of data, highlighting the challenges in maintaining model performance and avoiding model collapse as we move to training future generations of language models. Mixing a small proportion of real data with the generated data appears to mitigate model collapse significantly, aligning with our theoretical predictions. Overall, our experiments not only validate our theoretical results but also shed light on the practical implications of finite memory and capacity limitations in complex models, offering insights into how to better design and train future generations of models to avoid these pitfalls.